Okay. So yeah, it's 11:35, so I'm going to get started. This is June 4th. So we are here in sort of the lazy days at the beginning of summer, but try to stay a little bit on the ball. Only lab 3 due this week, but don't forget, right? I know it's not as exciting or as many marks as your assignments, but they're basically free marks just for doing a few exercises. And assignment 2 and the midterm are the same week, so plan accordingly. Maybe get assignment 2 done early so you can study. I am going to release a practice exam this week or next week. I'm not sure. Basically, the midterm, there's no surprises, right? Like 0 surprises. You take the practice midterm, study it. If you do that, if you understand everything that's being asked of you, you will do very well on the midterm. But if you don't study, of course, you won't. I think that's about it. Assignment 3, I will likely release over this exam break. So we're not allowed to have classes over the exam. This is technically a class if you look in your calendar, but it's canceled, okay? Because I have to basically, over the summer, they give me too many classes. So I have to cancel basically 2 of them. So that's going to be one of them. But yeah, that's about it, I guess. Any questions? It's like it's summer, right? It's this relaxed schedule. So like I forget about this class for a couple of days later in the week. And then I feel like I'm forgetting something. So if I do forget something, please remind me. Summer can be distracting. So today we are going to continue talking about linked lists, which are not super exciting. You've probably seen them a dozen times at least. We're going to talk specifically about doubly linked lists, but these are going to be the foundation of a couple of data structures coming up, right? So the singly linked list is going to be important for our skip lists, which we might get to later today. And the doubly linked list will be important for our space efficient linked list, which we will definitely get to today, and which I'll give you some hints about assignment 2 as well. All right, so when we left off, we were talking about singly linked lists. I just do a quick review. We're not going to go over all of the details, but just what are they good at? Well, a singly linked list is a bunch of nodes, and I only have a next pointer, right? So if I had a doubly linked list, I would have a previous pointer as well. But this means that if I want to, for instance, find a node, if I need to access this node in my singly linked list, I have to start at the head and walk through until I find it, right? I have a tail pointer as well, but that's only good for adding things to the back. As we talked about, I can push things on the back very quickly with this tail pointer, something like this, right? I just redirect some pointers and then I point the tail at this new thing, and everything's good. I have a longer list. If I try to remove something from the tail using the tail pointer, that doesn't work because I do not have a pointer that goes from the tail to the previous, and I have to be able to redirect this into null or nil or whatever. So on a singly linked list, if we wanted to make a stack, if we wanted to implement the stack interface, then we could push and pop not from the back, but from the front. We could push onto the back, but we can't pop really from the back. But we can push and pop very quickly from to the front, right? So push to the front, I make a new node, and again, I just move some pointers around. Pop from the front, I just redirect the head, and then whatever this is gets garbage collected. Maybe I return X if I like, or whatever. But once I'm done with it, Java will reclaim that memory, and then I have a new list that's a little bit shorter. Okay. Yeah, so this is the code for it. You can review it if you like. The other thing about singly linked lists is because we have, a head and a tail, which are just pointers, I end up with a few special cases, right? There's these edge cases that I have to pay attention to. For instance, if I push something onto my linked list, updating the head is sort of easy, right? If head is nil and I say u.next equals head, then u.next gets nil, and that's basically what I wanted to have happen anyway. But I do have to make this extra check to make sure, well, if I'm pushing something onto an empty list, then I also have to update the tail, right? So normally, if I have things in my list and I push something onto the head of the list, the tail is unaffected. But of course, if my list is empty, then I do have to adjust it. So we have these special cases we have to think about when we're using a singly linked list. The analysis, though, it's pretty good at these things. Push X is, of course, just a bunch of pointer manipulations. So it's O of 1. And pop, well, this is pop from the head. Again, pretty easy. We just redirect the head pointer. Although, again, we do have to consider what if I have one element left in my singly linked list. Well, then updating the head works, right? So now head is pointing to nil down here, but my tail is still pointing to this node that I want to have garbage collected. So I'm going to have to update the tail pointer as well so that this node and the data contained in it can be garbage collected. So again, on a singly linked list, for the most part, things work smoothly, but you do have a couple of edge cases that you have to check for. And so I would consider this like not as elegant as it could be, right? It's always a pain when you have to use a bunch of if statements to make sure that all your cases are covered. And it's nice when things just kind of work out for themselves. But so we can push and pop from the front of a singly linked list. We can also implement the queue interface, right? So queue means that, in this case, a first in, first out queue. So I'm going to basically add things to the tail of my linked list, and I'm going to remove them from the front, right? Because if I try to do it the other way, of course, I won't be able to remove quickly. So in the queue interface, this could be called add and remove, which is how we've been referring to them up till now. Of course, you might also see on queue and dequeue, especially some Java interface might use these. In Java, basically, often there's a lot of methods that do the same thing, right? So on queue and add will do the same thing. Dequeue and remove do the same thing. So on queue, again, I just add to the tail. We've seen we can do that. Again, though, we have this special case. If our list is empty, then we have to update the tail as well, right? Because tail is pointing to nil, not just the head. Sorry, if the list is empty, we have to update the head as well. But otherwise, we can just update the tail and then go. On queue, again, very fast, just some pointer manipulation. I don't have to traverse the list. Dequeue, well, this is basically our pop operation, right? So we don't have to write any new code for that. We can just pop off the front. So our singly linked list is good at the stack interface where we add and remove to the head of the list, and the queue interface where we remove from the head and add to the tail. So it's very fast at those things. O of 1 time for all of these operations. Okay, and I think that's about where we left off, but any questions? Okay, and it's up to you to write, I think, add, remove, and reverse or something like that on your assignment. However, a singly linked list is limited use. Again, it's a foundation of some other data structures. On its own, though, if you instantiate a linked list in Java, you're basically almost, or any language for that matter, you're probably going to get a doubly linked list, right? So doubly linked lists use a little bit more memory, but they're a little more useful as a result, right? So we can think of our doubly linked list. Now we have a previous pointer and a next pointer. So I have some data in these guys, and then this node, this is my next pointer. And here, this is my previous pointer that's pointing to nil, right? So that might be the head of my doubly linked list. And, I have B, whatever the node B is in, the previous points to A, and the next points to the node that contains C, and C points back at B, and C next points to nil. Okay, so this would be some version of a doubly linked list, but I mean, recall from the singly, maybe I have a head and a tail pointer for my doubly linked list. Well, now this is going to create a bunch of edge cases that are not difficult to handle, but they're kind of a pain and they make our code ugly. So in order to sort of handle all of this more gracefully, we're going to introduce a dummy node. So a dummy node is going to act as both the head and the tail of my doubly linked list. So now when I have a doubly linked list, it's going to look something like this. Right? Now I've put dummy at the beginning, but I could have just as easily put it at the back. In some sense, this is now a circular data structure. Right? So I have a dummy node here, D, and then I have pointers to and from whatever's previous, and pointers to and from whatever's next in my list, and it's connected all the way around. Okay, so sort of maybe symbolically, you could think of it as a circle. We're going to draw it like this. But again, whether the dummy's at the front or the back, it's the same thing. I have quick access to either the front or the back of the list, right? Using my next pointer here and my previous pointer up here, which points to the very last node in my doubly linked list. Okay. And we're going to see that this actually, especially in a doubly linked list, this avoids a lot of edge cases, right? So this is going to make our code a lot more elegant. And yeah, circular data structure. All right. Questions so far? Okay. All right, so our doubly linked list class is going to look something like this. I'm going to keep track of the number of elements with n. I'm going to have a dummy node. This dummy node is going to be both the head and the tail of my doubly linked list. There's nothing special about it other than it just has some null data in it. And it's a node, it exists. I can do things like check, does some node w.next equal dummy, right? So it's not like null, or, well, it is sort of like null actually, because null would be a single, depending on how it's implemented, it might be a single location in memory, a special null pointer. But yeah, I'm just going to check to see if this single dummy node is the one that's currently hooked up to this other node or something like that. We'll see. So my doubly linked list, this is my constructor. I'm making an empty list to start with. So n is equal to 0. Dummy is equal to a new node with some null data. And then dummy not next should be set to what? Yeah, I just want it to point to itself, right? So this is my empty list. This is what it looks like. I've got some fake data, but I could, technically I could traverse this list. I could walk through it from the dummy to the dummy. Yeah, this is what I want to have here. Okay, so we've created a list. We have the basic structure down. We want to implement get and set on our doubly linked list. So we didn't do this on our singly linked list. So the idea behind, if I want to get and set something, well, I'm going to use a little helper method called getNode, right? So basically, this is going to return a node. Let's say I get something at, this is index 0, this is index 1, this is index 2. So let's say I wanted to get 1. Okay, well, this get node is going to go and grab this node. This give me a reference to it. This node has the data in it, so I can, return. If this is node u, I can just return u.data. or u.x, whatever we're using here. Okay, so I just want to find the node and return it. And this get node function, well, we're going to have to walk through the list. There's no other way, at least in this implementation, to do that. You know, there are other clever ideas out there, like storing your nodes in a hash map, you know, or so where the data is the key and the value is the node itself. So then I can get back that node really quickly and then maybe add and remove from it very quickly. I was sort of toying with the idea of doing something like that for assignment 3, but I think we're going to go with skip lists instead. But yeah, so we have to walk through. But since we have access to the front and the back, and it's a doubly linked list, we can walk in either direction. Well, what I want to do is I want to check to see, is it closer to walk from the front of the list or the back of the list, right? So I'm going to say, well, if my index is closer to the front, it's less than n over 2, where n is the number of nodes, then I'm going to run this code, and we are just going to verify that this works correctly. So this is index 0, 1, 2, and let's say we wanted to get index 1. So if I ask for index 1, n is equal to 3, n over 2. I mean, this might return false actually, but let's pretend that it returns true, because it should, whether or not this returns true, this should work for any value I, right? Even if it's further away than I want it. So let's say I wanted to get number 1, code returns this node. Okay, so node P equals null. This is going to keep track of our current node. P equals dummy.next. So P is now pointing to here. P is pointing to index 0. So I'm going to run this loop. I is equal to 1. So J is less than I in the initial loop. So P equals P.next. So now P is pointing over here. Now J is equal to 1 on the next loop. Is 1 less than 1? The answer is false. So I'm going to exit out of the loop at that point. And P is pointing to the node that I wanted. Okay, so just a quick little verification. You're going to find I was fooling around with skip lists, trying to, well, I was trying to improve actually. I know I'm talking about skip lists, which we're not talking about right now, but we're going to get to maybe later. But the idea is I was trying to, you know, write a visualizer for it. So it visualizes the path through a skip list, which is kind of, it's a little bit technical in the beginning. Once you get used to it, it's fine. But getting actually the thing to print the correct path was bananas, right? So the theme a lot in data structures, especially for computer science, is think a lot and write a little, right? So you want to, before you start writing code, well, I mean, it's not bad to have a prototype, but at some point you have to sit down and say, okay, what is actually happening here? And draw these little diagrams and try to match them, you know, make sure that you match them to the code, right? The code is, it's not natural to read this until you've been doing it for a few years. Then it starts to read a little more, you get a little better mental model in your mind. But in the beginning, what you want to do, or what you want to have happen, is that I have some model here, and I want to be able to identify what happens when I apply this code to the model, right? So, and yeah, I was having a ton of trouble with it this morning. So I know if I have a few hours, I can sit down and get it all worked out, but I was busy with the slides as well, so I didn't have time to do it. Anyway, think a lot, write a little bit, write carefully instead of, for data structures especially. You know, if you're writing a website, you can just kind of blast through it, but data structures takes a lot of care. Okay. On the other hand, maybe I is not less than n over 2, so I want to, you know, we'll still go for index 1, but I'm going to walk backwards through the list, right? So there's 3 elements, so n equals 3, p equals the dummy, So we don't actually have, I have j equals n here. I don't actually have an index 3, or do I? Right? I mean, this is a list, and sometimes I want to insert something at index n, right? In this case, I would want to insert something at index 3, which means that, I mean, I'm out of space here, but I would attach another node here and then have it point to the dummy. So it is possible to insert at n, and so this code does accommodate that, right? So it is possible that this get node is going to return the dummy node, but in some cases that's what I want. Not necessarily in the get, but we'll see when we add something. Sometimes we want the dummy node so we can insert something before it. Okay, so p equals dummy, j equals 3, j is greater than I, j minus minus. So this p starts by pointing to the dummy, and then it goes to the previous. So now p points over here, j gets decremented to 2. Is j greater than 1, right? So I is equal 1. Is j greater than 1? The answer is true, so I get p equals p dot previous. J is decremented to 1. And then is 1 less than, or is 1 greater than 1? The answer is false. So again, I get to the right, I got to the correct node using this piece of code. Okay, so that's my get node. Again, there's a lot of technical details, and it's hard to orbit through a lecture, right? Until you sit down and work with this. I just want to give you sort of an inkling of what's going on, but if you're not drawing the connection, that's perfectly normal until you sit down and work it out yourself. But yeah, questions? Okay, so the main thing is that I'm going to take the shorter route to get to the node that I want. But if I have a get node function that works, then of course my get function is easy to write. I do an out of bounds check, sort of index check, range check, and then I just get the node, I return the x, which is the data element. And set, same thing. Again, I do a range check. If I'm out of bounds, I throw this exception. Here I have to do a few more moves because I want to replace the value in that node with a new value, but I also want to save the old value, right? So I'm going to grab the old value stored in y, and then I'm going to set the new value to x, and I'm going to return the old value. But in both cases, the code is now easy as long as I have a working get node method. Okay, so we looked at the implementation. Now we look at the runtime. So the running time of get and set, well, other than get node, everything is just O of 1, right? So, I mean, if you give me the node and say, give me back the data, well, that's easy. It's just one operation. And the same if you give me a node and I have to set the data, that's, it's like 3 or 4 operations, but it's still O of 1. So everything is very quick as long as I have the node. In this case, if I have to call get node, then get node runs in O of min of I or n minus I. Right. So if I'm running get node, it's going to be kind of slow. There are alternatives if you have you're storing the right data, and there's a bunch of other things that have to be correct, and you would have to consider, but there are other ways to access nodes in a data structure. Okay, so that's get and set. Of course, we're implementing the list interface, and the other two main methods in the list interface are add and remove. So, but if I'm given the node, then add and remove are simply manipulating pointers. So let's say I wanted to add x to some pre-existing doubly linked list. Well, I make a new node, and then I'm going to move some pointers around. So this what is this? This node next is now pointing to the node of X. And this previous pointer, instead of pointing at A, now points to the node containing X. And my node, let's call this U. So U.previous now points to A, and U.next now points to B. And then I have X is now just a part of my doubly linked list. Okay, and so that's sort of easy. And if I wanted to remove a node, I'm basically going to do the same thing. So let's say I wanted to, this was at index I. So somebody gives me the node at index I. Well, all I'm going to do is redirect a few pointers. So this A.next, instead of going to X, is going to go to U.next. And B.previous, instead of going to U, is going to go to U.previous. So yeah, it's sort of a lot of hand wavy, but that's the basics behind it. So we'll look more specifically at exactly what we're going to do now. With the add function, again, the same as get and set, we're going to use a helper function because we can make use of it across a bunch of different scenarios. So we're going to have this add before, where I give you a node W and I say, insert this piece of data X in a node previous to node W, right? So when we look at this drawing now, this is my node W. I give you a reference to that. And then I say, make a new node, put X in it, and insert it before W. Okay, so what do we have to do? Well, we've seen sort of the pointers. Right now I have, this is W, this is W.previous, which I got by following this pointer. And W.previous.next, well, that just points back to W. So I want to adjust all of these pointers. And well, let's take a look at the code and then try to match it to what's going on here. So basically, the blue arrows in this diagram correspond to these statements, right? So let's take a look. So if I want to just insert the blue arrows, this is node U, which I've already made. I'm going to say U.previous equals, and this is W.previous. Okay, and we can see here, that is the first thing that I write. The next node, well, this is, what is this? Well, I mean, we can see it right here. This is W.previous.next. That gives me this pointer here, and I want to point that at U, which I do in this next statement here. Right? So it's a little bit, the .next, the .previous, blah, 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 is a little bit hard to track, maybe just in your brain, but if you draw it out in a little diagram, it makes it a lot easier. And then I have my other two pointers. I have W.previous. I want to point that at U. So W.previous equals U, and then U.next equals W, which I have up here. Okay, so that's it. I draw a little diagram. I label my nodes, and I know that these blue lines are the things that I have to redirect. So I go ahead and do that. At this point, I've added a new element, so I increment N, and I can return this node. It might be useful in some context. Okay, questions? All right. What happens if I do this backwards? In other words, what if I say U.next equals W, W.previous equals U. I have that up here, and then I run these two. What's going to happen? dot next equals W. That's pretty harmless. That's this one here. W dot previous equals U. I've done this one. And now what? Well, now W dot previous is no longer this node. W dot previous is this node. So now I've disconnected my linked list. Okay, so it's easy-ish, right? As long as you don't make any devastating mistake. And this would be, of course, very difficult to find if you're trying to debug it, because now your linked list is suddenly detached. Or, what would actually happen is if I'm searching this way and I'm looking for X, of course, I never find it. If I'm coming this way and I'm searching for whatever this guy is, again, I would never find it. Yeah. So it's one of those errors that would persist for a while until you actually did the right combination of things that it broke, and then you're wondering, why doesn't my data structure work? Yeah, questions? Yeah. We're forward thinking here, right? So yeah, maybe we don't need it. In a lot of cases, we probably just discard it and ignore it. But there are some cases where maybe like an iterator, like if I have an iterator and I want to insert something into my, maybe some iterators don't let you do that, but maybe this one does, lets me insert as I walk through, then I still want to have a reference to where I currently am in the list, right? So, yeah. Other questions? Yeah, sometimes that's an excellent question because, yeah, why do we have this? And it's a lot of times we're going to throw it away, right? We're just going to ignore it, but there are circumstances where it would come in handy. Okay. All right. Well, that's great. It works in the general case, right? But we haven't talked about the edge cases, which is where a lot of the things possibly could go wrong in a singly linked list, right? We had to update, and we had to do checks to see if our list is empty and then update the tail pointer. What happens if, well, let's see, what happens if we're removing something from the head or the tail, or adding to the tail, right? So now I want to add something in the last location in the list. Well, now my node W is just the dummy node, right? So this, I pass in, W is equal to the dummy node. So when I say U.previous equals W.previous, that's just basically dummy.previous, which is still this one. W.previous.next, well, W.previous is still this one. .next still gives us this pointer. U.next equals W. Well, this is now pointing to my dummy, and W.previous equals U. Now my dummy is pointing to node U. So my edge case now just works, right? Where I'm adding to the back of the list. I don't have to worry about updating special pointers or anything like that. It just works. And the same if I'm adding to the front of the list, right? So now dummy, I want to add something before this is previously index 0. I'm adding I'm adding X to index 0. I make a node U, and now the previous is W.previous equals dummy. So, well, U.previous equals W.previous. Well, this is just now pointing to the dummy node, which is what we wanted. W.previous.next, well, that's just this pointer here. Again, it's exactly what we wanted. U.next equals W, of course, these still work just fine. So again, having the dummy node there eliminates all those edge cases. I just have one case now. And the one case is just redirecting 4 pointers. I guess there is one more case. What if I'm adding to an empty list? Do I have to do anything special? So W is, of course, the dummy node in this case, right? So I'm adding before the dummy node. In this case, it looks like I'm adding after, but again, this is just the way it's drawn. I could have easily drawn the dummy. Maybe I should have, but regardless, W is dummy, so U dot previous equals W dot previous. Well, on my empty list, the dummy is just pointing to itself. So W dot previous gives me, this is my dummy node, and dummy dot next equals U. That's this blue one here. Yeah, U dot previous equals dummy. That's fine. That's my first line. U dot next equals W. That is just this pointing to the dummy node. And W dot previous equals U. That's this pointer here. Okay, so again, even if I have an empty list, everything just works if I have a dummy node. And I, initialize it correctly. All right, questions? Okay. Okay, so now add, I'm going to do a range check. I'm going to get the node at index I, and I'm going to add before that node, right? So maybe this diagram is no longer the best, but if I imagine these are doubly linked lists, so I want to add 2x, and then I have a dummy here. Well, I want x to be at index 2, and maybe this is y here. So I want to make a new node, and I want the new node to go here. And now this is going to be index 2, and this is going to be index 3, right? So I get the node at the index exactly where I want to insert, which returns this, let's call this W. I add x before the W, and now the x node takes the place in the list of the y node, and the y node gets pushed one location greater. Okay. All right, so that's, once I have add before and I have my get node, then add is really, really easy. Questions? Okay, so it's dominated by this get node. Once I have the node, everything is very, very fast. It's O of 1. Of course, the get node, I still have to walk through the list. And I take the shorter path, but it's still big O of the min of I, or n minus I. Remove, same thing. If I give you a node, I asked for it to be removed. Well, I'm just redirecting some pointers. These guys now replace all those with these two blue pointer. Right? So this node U, and so I might say something like, well, let's see. I want U dot previous dot next to equal U dot next. So something like this, U dot previous dot next equals U dot next. Again, it looks confusing, but if you make a little diagram, then hopefully it's a little bit easier. You can see that this is where I previously was. I wanted to point it, sorry. This was where I previously was, and now I want to point to here. This other one, well, this is simply U dot next dot previous equals U dot previous. Right, and then I basically, these two blue pointers, I've stitched the node U out of this list. So yeah, again, the blue arrows correspond to one of these statements. Once I remove the node, I can decrement n. Yeah, questions? Okay. So now I have this remove node function. So when I want to remove something at index I simply get that node, then I remove it. And oh, the nice thing is I want to return it at the same time, and I still have a reference to it. I can return that data, and then that node gets garbage collected later on, as long as it's not referenced somewhere else. Okay. Again, the remove function, the same as add, is dominated by this get node. I have to walk through the list to find the proper node. Once I have that node, everything runs very quickly, but since I do have to get the node, it's big O of the min of I or n minus I again. So yeah, that's our doubly linked list. The size is, of course, O of 1. Everything else, get, set, add, remove, is kind of slow, right? This is, I mean, it's the min of I or n minus I, but it's still going to be basically, in some sense, O of n. But we can use this mixed with other data structures to get, to make some trade-offs about, we'll see. We're going to make trade-offs to get better space, but also maybe a little bit faster add, remove, get, and set operations. But yeah, questions? Yeah. So the key takeaway, dummy node makes everything nice. But yeah. So let's see. Again, we have a doubly linked list implementation, and Java has a doubly linked list implementation. And let's see. I think I have to rewrite this, but won't take very long. So again, this is just code from your assignment 1 that's just going to time a bunch of operations. Here we're going to add to the back of a list, which will be either a doubly linked list from the ODS library or one from Java. So this will be a linked list from Java. And this should not be array list, I believe. Might have to look this up. Yeah, they do have a linked list implementation. Okay, so that's the Java linked list. Down here, we want the doubly linked list. Test. So it needs to be a list. Sorry, just give me 1 second. Of course, I didn't check this correctly. Doubly linked list from ODS. Seems like oh, I don't need the class. All right, that's good. So I have an extra argument there. Okay, so we're adding to the back, which both should be very fast at. And then, let's see, ODS. Test. Yeah. I have to give it some arguments, in file.text and out file. Okay, so the Java linked list runs in 0.2. Guessing, I still don't know I still have to look up the proper units for that. Is something, some seconds, tenths of a second or hundredths or something. Doubly linked list is faster. We can try something a little bit bigger. Generate. I'm not sure what it has, but let's try 100,000. Run that again. Again, our doubly linked list runs faster, at least adding to the back, right? Which both of them should be fast at. Again, I'm not sure why. Java maybe does some extra stuff that we don't for Java the built-in libraries might be a little bit safer. They might do a little bit of extra overhead to build it. So it might not be, it might be if we went high enough that this difference would disappear, but who knows? Let's try, just for fun, let's try 1 million. Yeah, it's still faster. Okay. We could try adding, let's try. Oh, this is removing from the front. Let's try removing from size over 2. So now we're removing from the middle. This might take a while. I forgot I had 1 million things in the in file. All right, maybe we'll go with something a little smaller. Start with 10,000. Ours is still a little bit faster at 4.8, and theirs is 0.66. Let's try 100,000. Ooh, now it's slowing down. Huh. All right, so kind of even on removing from the middle, pretty close at least. It's a lot slower than adding and removing from the front and the back, which we would of course expect. But yeah, questions? Okay, I put some of this code up for you guys. You do have to download the ODS library from the opendatastructures.org website, but it is up on the, some of these tests, and again, they're very rough, right? So, don't expect something polished, but they are up on Brightspace. Okay. Okay, so singly linked lists, doubly linked lists, and now we're going to look at space-efficient linked lists. So we looked at all our array-based data structures, and we, saw what they were good at and what they weren't good at, and then we had the rootish array stack, which was a space-efficient implementation of an array-based data structure. But now we're going to make a doubly linked list more space efficient. So currently our doubly linked list, we didn't really analyze the space, but I mean, it's fairly easy to see. I have a dummy node, which, okay, I don't really care. That's only one, that's O of 1. But if I have a data element here, for each data element, I have a previous and a next pointer. Okay, so if I have O of n data elements, then I'm wasting pointers, wasted space. Always, even if I'm only storing a few things. So we're going to try to improve that. Yeah, all right. Well, this was, I mean, not super relevant, but I thought it was a funny quote because it does seem to be true. Now, there's 2 ways of constructing software. One is to make it so simple, there are no obvious deficiencies, and one is to make it so complicated. I mean, I'm not judging anybody because I've done both, right? But yeah. the older I get, the more experienced I get, the more simple seems to be better. Abstractions are great, but complicated design patterns sometimes just get in the way. Yeah, so we're primarily concerned with speed with data structures, but sometimes we want to have a space-efficient data structure as well. So we saw that with arrays, we could have, basically we have an array and part of it might be full and the rest might be wasted. We tried to sort of trade off on that idea by having a list of arrays, and each array in the list got a little bit bigger so that proportionally we were only wasting a little bit of space. Right? We're going to do something similar, but our trade-off now is going to be more fixed. Right? We're not going to have the root array stack was nice because no matter what n was, we had O of square root n wasted space. Ideally, we would like the same thing here, but this is not going to be dynamic. We're going to choose a parameter b, and parameter b is going to define how much space we waste. So in this case, it's going to rely on n, which if we don't know up front, it's going to be hard to construct an efficient data structure. But if we know n up front, then we can define this so that it doesn't waste a lot of space. Right? So the idea with linked lists is that each node contains one piece of data and two node pointers. So we're wasting this 2n of space. So we're just going to try something very simple. We're going to take this doubly linked list, and we're going to just stuff more data into each node. Right? So for this contained one thing, maybe now this contains a pointer to a list of things. And that's the idea. So if we stuff more data into each of these nodes, then of course the ratio of data to pointers goes up and we save on space. So what that means is that we need, the same as before, we need some sort of intermediate data structure here. Now we're just going to loosely call it, we're going to call these blocks for now. A block, a node is going to be sort of interchangeable, right? So I might refer to this as a node, or I might refer to this as a block, block as in a block of data. All right, so now each node contains a pointer to a block of data, along with a next and previous pointer. So I'm going to have a doubly linked data structure, but just going to change what type of data we're storing. So what sort of challenges are involved in the get and set operations now? If I wanted to do something like this, and the add and remove, right? So let's think about this. So, I mean, let's not get too complicated, but let's say I have this, and I'm storing some data elements, A, B, and C. And this points to, we'll just pretend that that's a double arrow. And this points somewhere else, and this may be X, Y, and Z. Okay, so as before, I have these intermediate data structures, and of course, they'll have their own index. Probably they'll implement the list interface. But so I'm going to have the indexes that I want for each of these data elements. But also, these data structures have their own indexes. Right? So when I get and set, sort of like with the root array stack, I'm going to have to translate one set of indices to the other. Right? So when I say get I, well, now I means what? I means, well, I got to figure out which block I'm in, right? So if I call get 4, then I should return this block and the element y from inside of that block. So I want to return this block and the whatever's at index 1 in that block. Okay, so I'm going to have to do these sort of translations again. If I called get one, of course, that's a little bit simpler because I'm going to get the first block and index one into the first block. But either way, this get I and set I, I'm going to have to translate that I into some block and some index into that block. Okay, so that's the challenges for the get and set. Add, well, add or remove. Okay, so let's say I add and remove. That shouldn't be too much of a problem. If I can translate these indices, I could say add, W to location 4. So now W is going to go here, and then Y and Z will get shifted. And then maybe I add a few more things, but so at what point should I make a new block, right? If I just keep adding to this one block, then what's the point of having a blocked list, right? I'm just going to have one single block with all the data in it. Then I'm not really going to gain anything. We haven't talked about exactly what we're going to gain here yet, but there is something to be gained by dividing it up like this. So add, remove. Also, if I keep removing things, and now this block is empty. Should I remove this block now? Right, so these are the considerations, the types of considerations that we're going to have to figure out to implement this. Do you have questions? Okay. So the size of our block is going to affect our implementation, and how much flexibility should we have in the size? Well, in this implementation, we're going to make things simple. We're going to choose a parameter B upon creation. I think this is similar to assignment 2, right? I'm trying to remember the exact spec, but I do believe we have a block size in assignment 2. We're going to choose a parameter B when we create our space-efficient linked list. And then we're going to limit each block to a maximum of B plus 1 elements. So basically, we want each block to have B elements, but we're going to have to be a little bit flexible, right? So that if we're not flexible, then we're probably going to have to do too many operations to keep our list together. We're going to allow a maximum of B plus 1 elements. And, we didn't talk about it, but we have a maximum of B plus 1 elements. And if this one is full and this one has room, well then, when I add something to this one, maybe X, I could shift some element out of this current block and into the next block, right? If this has only B elements and this has B plus 1 elements, and I want to add X to this B plus 1, well, I said that's the maximum. So I can't really add X, but if there's room beside me, I could just shift one thing over. And if I'm using an array deck, that's a fast operation, right? I remove from the back and I add to the front of the next one. These are both very fast operations. So I can do this quickly, and then my add operation is not too terrible. So we're going to take an array deck, and we're going to create a bounded deck class. Bounded because it's going to have a fixed size backing array. Right, so our backing array is going to be, each backing array is going to have B plus 1 locations. All right, questions? Okay, so our bounded deck, so this is our space efficient list class. Inside, we're going to have an inner class bounded deck that extends array deck. And inside here, well, we have to give it a type so that we can make these primitive arrays. Not primitive, sorry, but generic arrays. We're going to make a new array of size B plus 1, right? F is, this is the factory, right? And, well, the other thing, I want to reuse all these, the add, remove, get, set, but I don't want it to be resizing. So our old implementation would resize. I want it to stay at size B plus 1, and I'm just going to make sure that I don't add too many things to it. right? So we're going to override the resize operation and just leave it blank. So when it gets called, when I add something, it might get called, but I'm just going to ignore it. More likely on remove, but okay. And then given this bounded deck class, I'm going to make a node. Now we're going to reuse all this doubly linked list, the doubly linked list data structure that we just learned. So we're going to reuse all those things. But now our node is going to be slightly different. Instead of some generic E type of element, I'm going to make a bounded deck. It's going to store my data for me. I'm still going to have the previous and the next. And then, yeah, I want to keep track of how many things are total in my list. And like our other doubly linked list, I want to have a dummy node. Okay. Questions so far? Okay. All right. So tight restrictions on the number of elements in a block. We're going to have some rules about our space-efficient linked list. If there's only one block, right, so we always have this dummy node, that's fine. So if it's empty, we still have a dummy that points to itself. But maybe I add a few things to it. The block size is fixed. So as soon as I start adding, I'm going to have to make a new block, add it to my doubly linked list, and then add things to that block. Now it has size b plus 1, but if I add one thing, then most of it's going to be empty, and I'm just going to have to put up with that, right? So my last block, or if I only have one block, this might be empty or almost empty, which is unavoidable. Or maybe I have multiple blocks, right? So if I have one block, then it contains up to b plus 1 elements. If I have a bunch of blocks, then the last block might be partially empty, right? This one maybe has one element in it or something. But this guy up here definitely we're going to be a lot more strict about how many things it holds. It's going to have at least b minus 1 elements and at most b plus 1 elements. So each of these blocks, except for the last one, stores b minus 1, b, or b plus 1 elements, no exceptions, right? So if we sort of go outside those bounds, then we're going to start shifting things around. All right. So now, what does this mean in terms of space? So my space-efficient list contains n elements. Then we can look at how much, we're going to look at how much space we're wasting. First of all, we have n over b minus 1 plus 1 blocks. That's the most we can have, right? If all of our blocks have the least amount of elements, and I have one possibly nearly empty block at the end, then, sort of ignoring the constants and rounding off, I'm going to have big O of n over b blocks. But I want to do a rough sketch here. I think that should be pretty clear, but, I would have b minus 1 here, and b minus 1 here, and b minus 1 here, and then this guy might have 2. But altogether, I have roughly n divided by b minus 1 blocks. Okay. So we have this many blocks. So how much space is wasted in these n over b blocks? Well, each node has 2 pointers, right? So I have my previous here and my next here. Those are considered wasted because they don't store data. So at least O of 1 per node, plus whatever is wasted inside here. But of course, if we're in the middle blocks, we're really strict, right? We're wasting at most 2 locations. We might have 2 empty locations in those inner blocks. So my last block might be empty, and I'm going to waste b plus 1 space. This guy, I have 2 pointers, maybe 2 empty data locations. That's 4, I'm wasting 4 memory locations per block, plus the last one. All right, so yeah. So I have O of 1 wasted space per block. Other than the last block might waste b plus 1, O of b plus 1 plus the 2 pointers, but it's still big O of b. I have big O of n over b of these blocks, so my wasted space is the last block plus, the other blocks are wasting less space, but they still waste a little bit. And there's n over b of them, roughly. All right. Questions? Okay. I had sketches in mind when I was making the slides, and now I completely forget what they are. That's fine. Okay, so this is our wasted space. What is the best choice for B to waste the least amount of space? Let's think about a couple of edge cases first, right? So what happens if I choose a very low B? So let's say B equals 1, right? Then I'm wasting O of 1 plus n over 1. This is O of n space. Okay, so that's, but I mean, that's not great. I can do that with an array list or an array stack or whatever. If I choose a block size equal to n, right? I don't really know n maybe, but maybe I do. Let's say my block size is equal to n. This O of b plus n over b plus n over n, which is again O of n. So if my block size is really small, I'm still wasting a lot of space. And if my block size is really big, I'm still wasting a lot of space. So yeah, what's the optimal? What's that? It is square root of n. Let's talk about why it's square root of n. So basically what I want, on the one hand, if my block size is too small, this gets big. On the other hand, if my block size is too big, then this is big. So I kind of want to balance these two things. And basically, I want b to be equal to n over b. And that's going to give me my middle ground between a small block and a big block. So what does that tell me? Well, I multiply both sides by b, I get b squared equals n, and then I take the square root of both sides, and b equals square root n. Okay, so that's how I can figure out, if I know my n, I can choose a b that's square root n or close to it. And then this is a space efficient list. That's the best we can do. Any questions on that? Okay. So as b goes up, n over b goes down, and vice versa. So when we choose to have these two about equal, we get b about square root of n if we know n beforehand. And so our wasted space is big O of square root n. And this is a lower bound, right? We showed that with the root-ish array stack. If we are able to add things one at a time, then at some point we have to waste square root of n space. So if we know n in advance, this is optimal. Okay. All right, so that's the rough outline of our space-efficient linked list. 1244. And we've shown that if we know how much stuff we're storing, then we can make it efficient. We're going to see actually that this will make our get, set, add, and remove a little more efficient as well. I think I might break early before we get into implementation because I don't know, there's a lot of details there. We'll take a refresher we'll come back at 1 o'clock and get into those details. So yeah, we'll break here. I'll be back at 1. We'll talk about space efficient linked lists, and then probably we'll get to skip lists, which are, well, I don't know. I like skip lists. They're a lot of fun. Maybe you'll like them too. Probably. I don't know. Maybe. But yeah, I'll see you guys at 1. All right. So yeah, 1 o'clock, yeah, right on time. Okay, so we're going to talk about the implementation. And again, this is, there is I'm gonna, after this, I'm gonna talk about assignment 2 a little bit and how these two things are related and the lessons that you can take from this. But yeah, there is an addendum that mentions, you do not need to spread or gather in the assignment. There are spread and gather methods in this class. You don't need to do that. The assignment 2 is very similar, but it's in some sense simpler than this space efficient list. But yeah, so implementation now. So we've figured out the overall structure of our space efficient list. And we've talked about how we can sort of be optimal on space if we know how many things we're storing. But now we actually have to implement this thing. And again, it's one of the biggest initial challenges is to take some index I and figure out which block I get back and which index into that block there is, right? So given an index I, I'm going to define another class called location. That sort of makes this a little bit easier for me. So this location is going to store a node from my list, as well as an index into that node. So that means, why not just grab the data element? Well, again, because, if I have a reference to a node in a linked list, then there's a bunch of operations that are available to me, like insert a new block right behind the old block if I run out of space, for instance. So yeah, we're going to grab the node, even though it might appear at first glance that we don't need it. We're going to need it later, and then an index into that node. So then if I'm given a location, I can grab the data out of it, or I can use the node and do something else. To find this location, we're going to start at the closest end and walk, right? So, well, it's sort of simple enough. Let's say I have a space efficient list, and maybe there's B minus 1 and B B plus 1 elements here. And then maybe the dummy is here. And I want some index, get I, for instance. Well, it's a doubly linked list implementation. So to find the correct block, I'm just going to have to walk there, right? So again, I want to check to see, if I'm, maybe I'm doing this out of order a little bit. Yeah. So this is my location class, first of all, and then we will talk about actually finding it. So I'm going to grab some node, find the node where my element is being stored, and I figure out the index into that block. Okay, so I have a block, I have an index into that block. I initialize both of them, and then, by default, everything is protected in Java, and this location will be also part of my space efficient list class. So I'll have basically access to all of these data elements. So if I want the actual thing, the piece of data, I can easily get it from the location. Now I just have to get a location, which, all right, so it's a linked list, doubly linked list. And let's say I have B plus 1, B, B minus 1. Let's give these some numbers, actually. Let's say this is B is equal to 10. Let's say I have 9, 10, 11. And this is the dummy, in front. And it's also linked to the back. And I say, so this is 9, 10, and 11 is the number of data elements in each of these blocks. And I say get 21. Well, and let's say that there's a bunch of other blocks here that I don't want to count. But let's say, so I'm going to decide if I should start at the front or the back, right? As tradition in my doubly linked list, if it's shorter to go from the front, I want to do that. If it's shorter to go from the back, I want to do that. But assuming that I want to go from the front, then to get index 21, well, I'll say I equals 21. And then I say, well, is I less than the block size of my current block? And the answer is no, right? So 21 is greater than 9. So I'm going to subtract 9 from 21. I'm going to get 12. And that means that I've skipped over all of these guys. And then I'm going to update. I'm going to walk to the next block in my list and say, well, is I less than 10? Right? So, and the answer again is no. So I'm going to subtract 10 from 12, and I'm going to get 2. And then I'm going to skip all of these, and I'm going to look at the next block. I'm going to say, is I less than 11? And the answer is yes. So that means the element I'm looking for is at 0. I have to be careful about this. Yeah, it would be at this index. Right, so I is 2, it's in, so now I know the block and I know the index into that block. Just through some very simple math, I'm going to walk through my linked list and subtract the size from I each step. Okay. And that will take me to the correct block and also get me the correct index into that block. Right, questions? Okay. So yeah, while I is greater than the current block size, and yeah, this code is a nightmare. Pat loves the variables that are a single character. I can't stand them, but I use them because they're in the textbook. Maybe I should change the slides to be more descriptive. The problem is if I change them to be more descriptive, I run out of space on the slide, and it's just a pain. But so yeah, you kind of have to, you got to do some mental translating here. U is a node, D is the data in that node, which is a bounded deck, dot size. So that's the number of data elements in that block. So while I is greater than that, I simply subtract the size from I, move to the next location. Once this returns false, I have my I, my U points to the block that I want to be in, and my I has the index into that block. Going the other way, if I decided, well, it was easier to start at the back, well, I'm going to start at the dummy node, and then I'm going to say IDX equals N. So if let's maybe do a quick version of this. This is 10, 11. And let's say I want, let's say index 14, so get 14, but I'm going to walk from the back. Well, I'm going to have this temporary variable that points to, what is this, 30? So IDX equals 30. I have 30 elements in my list. I want to get number 14. While I is less than IDX, I subtract the size, right? I say, well, is I greater than or equal to IDX? The answer is no. So I want to subtract some stuff from here. So I'm going to subtract 11 from IDX, and then my IDX is going to be 19. And then I'm going to say, well, so that means I've skipped over these guys. And now I'm looking at this block, and I'm going to say, well, is I my index less than this? The answer is no, so I'm going to subtract 10. I may have done that a little bit. Here, let's look at the code. Yeah, I moved back first. Sorry, yeah, because I start at the dummy. So similar to what we have here, except that I step into this and I subtract the 11 at the same time. And then I say, is this less than? So now my IDX is pointing here. And I say, well, if I is greater than my IDX, then I is going to be in this current block. But while it's less than the IDX, I still have to walk backwards. Right? So in the next step, I subtract 10, IDX is 9. My pointer is now, my IDX is here. My U is pointing to this block, and I say, well, is I less than the IDX? And the answer is no, which means I'm going to find I inside this block. A little more complicated coming from the back. Same principle, but yeah. And so then at this point, to get my actual index into that block, I'm going to subtract. If we look back here, I want 14. 14 is in here. I want to subtract everything in this first block to get my index. Okay, so that's what this last part here is. All right, questions? Yeah, it's pretty ugly. If you sat down and wrestled with it, you do this one first because it's easier, and then you can kind of use what you learned up there to figure that one out. Okay, so that is get and set. What is the runtime? Well, it's not too bad because we're skipping, or at least it's better than a doubly linked list by itself, because we get to skip a bunch of things at once, right? So instead of walking one data element at a time, we're skipping about B every time we take a step. So every step gets us B minus 1 indices closer at least, except maybe the back is still partially empty, so maybe that one, maybe we have to take a step and there's only like 3 elements in there or something. But we're going to reach node U in I steps from the front, but we're skipping B at a time, so I over B steps forward, and then just a little math to get the index, or N minus I over B steps backwards, right? Again, we want to move N minus I steps total, but we're skipping B, we're taking B steps at a time. All right, so get location runs in big O of the min of I or N minus I over B. And yeah, so depending on B, not only do we have a space efficient list, but actually this might be faster at finding stuff as well. All right, and then once we know get location, get and set are pretty straightforward. I want to get something. I do some bounds checking first of all. Then I get the location of that element, and then I return location.u is the node, u.d is the bounded deck, and the bounded deck has a get function or a get method, and I use the location.j, which is the index into that block. Okay, so conceptually easy. This code gets a little bit ugly, but yeah, questions? Set, same basic thing, except of course, I still have the extra steps, but those extra steps are done for me in the set. So my traditional set method, I want to save the data element into a temporary variable and then return it at the end. But my bounded deck inside implements the list interface, and it has a set method that's going to do that for me. So I just return whatever is returned by this set method. Okay, so those are my get and set using get location. And obviously I'm doing almost nothing in both of these. Get and set in my bounded array deck are constant time. Those are O of 1. So all of the work is being done in this get location where I have to find the correct node. And that is big O of min of I or n minus I over b time. Okay. Questions? All right. Adding gets complicated. So that's get and set. The big thing there is the translation, but it's some pretty simple math. For your assignment 2, you of course have to do a similar translation. When we ask for get and set, you're going to have to walk through your blocks, basically doing the same thing we did here, right? Just subtract as you go, or in reverse, you have to, use your IDX. Again, the code is in the slides and in the textbook, and you're free to use it. You're actually free to even space-sufficient linked list as part of the ODS library, so you can actually just take that code and adapt it to your usage, whatever you want to do with it. You're allowed to do all of those things. Okay, so add more complicated. So we're going to start with a very simple case. We're going to add to the back. So add x adds to the back of the data structure. By that we mean the nth location. Okay, so obviously if the last block has space, well, I guess we're not really showing that here, but if I have b plus 1 here, and then I have b, and this is my dummy, and this is all I have, well, I actually have space to add at the back, right? So I'm going to add x to my last. I'm going to get the location. I'm going to add x to the back of that bounded deck, and I'm still fine with my space-efficient list. I don't have to do anything. I don't have to add a new deck or shift anything or any of that. But it is possible that, well, next time I add something, now the last one is full. I'm not allowed to have b plus 2 elements, or maybe I just have a dummy node. Right? Maybe my list is completely empty and I'm adding the very first thing to it. So in this case, I'm going to make a new block. I'm going to add it to the back of the doubly linked list, right? Which is fairly straightforward, a bunch of pointer manipulation. And then I'm just going to add to that new block. Okay, so it's kind of being blocked by this thing here, but I'm adding, there's a full bounded deck at the back. I want to add to the back. Well, I'm going to first add an empty block, and then I'm going to add x to it. So yeah. Last, I'm going to grab the last block. If the last block is full, or if there's nothing in my list, I'm going to add before dummy, right? And this was the question that came up before. Add before, why do we return a node? It wasn't useful in the doubly linked list case, but now when we're doing a doubly linked list of blocks, it is useful, right? So now we return the node that we added, which is the new last, and then we can add x to that new node, right? So hopefully that's clear. I either have this case where the last block is full, or I just have the dummy node where it's pointing to itself. So in this case, I call add before dummy. It makes a new block that's empty and hooks it up correctly, and then and returns it. So now I have this nice empty block. I just add x to it, and I'm done. Questions? Okay. So that's add last. Adding to an arbitrary location gets a little more complicated, right? So today is a bit of a technical day. So this part is a little technical, and then if we'll probably start on skip lists, which are quite technical. They're nice though. Once you understand them, they're not as bad as you think. Very hard to write code for, at least in my experience. I have to think a lot before I do something. But anyway, I want to add to an arbitrary location. Well, get location is going to, this shouldn't be, should be a location, eh? Okay, so I have a location. It has the node in it, but yeah, technically wouldn't run, of course. So what do I do? Well, what could happen? Let's say I want to add something and I'm adding it here. Well, maybe there's space. If there's space, I just insert it and I'm good, right? If there's less than b plus 1 elements in that block, I'm okay to add one. Maybe it's full. If it's full, then, well, these are decks. Maybe I can shift an element from one to the other. If there's space beside me, I can shift one. And if I do that, then I can add to my current one and I'm done. Maybe I can shift it a whole bunch of times, right? But I should think about how many times I'm shifting it. In your assignment, there's no limit. You should shift right to the back. But in the space efficient list, we're going to put some bounds on that as well, just so we get better performance. So if the block is not full, we can add to it. That's not a problem whatsoever. But what if my current block is full? All right, so these are array decks. Let's say I'm adding to this one, this block U of 0. It's full, and also this guy's full. But there is a block that is within some acceptable distance that does have room. So what I can do is I can just shift. These are array decks. Each of these shift operations is very fast. So I shift one element from here into here, and then one element from here into here, and then finally one into that last block. Okay, so we add an element. If our current block is full, we're going to search for a block that has room in it. So yeah, scenario 1, there's room in this block. Scenario 2, there's no room in this block, but I look down the list and there's a block within an acceptable distance with room, and I just shift everything over. But yeah, the question is, how far should we look? And what happens if we go too far and everything is full? So if we go too far and everything is full, well, what we're going to do is we're going to add a new empty block, and we're going to shift everything around so that now everything has space, but everything is still within the proper bound. So that's the idea. So yeah, if we find one not too far, we can make room. If we look too far, well, what happens? We have a small block size. These are quick, but if we have enough of them, then it's no good, right? So if we have more than, again, the trade-off is when B is equal to N over B, right? And so if now, when we add something, adding is something greater than O of B, considering if B is root N, then that's kind of poor performance. We want to avoid that. So instead, we're going to do a major restructuring. So again, we're going to do, every once in a while, we're going to run out of space. We're going to have to do a major restructuring. It's going to cost a lot. We're going to amortize it, right? So that's the general idea. Okay, so 3 cases for adding an element. One is I look at B steps. I'm trying to add to this current block here, U of 0. And I'm going to look B steps to the right. And if I find a block that has an extra space within B steps, then I'm going to shift all of the elements over, make some room in this block. I'm going to insert into that block, and I'm done. Okay, so that's case number one. Case number two, I'm looking for space. I don't find any space, but I find the dummy node within B steps. Okay, so now I know for certain I don't have space, so I'm going to add a new block that's empty. My last block in this can be partially empty, so I don't really care if it only has one element. That's allowed. So, and then I'm going to shift one element in here, one element in here, and then one element, empty one. And yeah, so I have an empty one. I shift one element from U of 0, this empty block. It's the last block, so the fact that it only has one element is okay. And then I'm going to insert X into my U of 0 block. Okay. All right, so those are the two sort of easy, straightforward cases. The third case is where things get a little more complicated. All blocks within B steps are full. So here, I'm specifically saying B is equal to 3. We're going to do a little mini example, which means each of my blocks can hold up to 4 elements, right? So B plus 1 is equal to 4. So each of them is full. They have 4. I'm trying to insert or add whatever, let's call it 0. But everything's full up to B blocks away, which is, in this case, 3. So I'm full, neighbor's full, U2 is full. Afterwards, there might be space, but I don't care because that's too far. I'm going to lose performance. So I'm going to insert a new block after this last block that was full. And then I'm going to shift all of these elements around so that each block now contains an acceptable B items. And how do I know that this works? Well, because I know exactly how many blocks I have, and I know exactly how many elements in each block, right? I have B blocks, and I have B plus 1 elements in each block. And if I take those B blocks, right, so now I had 3 blocks, and now I have 4 blocks. My 3 blocks had 12 elements, and if I distribute those 12 elements over my 4 blocks, now each block has 3 elements, every block has space, and every block is within my bound, right? It's exactly B. So I take B plus 1 elements in B blocks, and so that's, basic math. I have this many elements, and I'm just distributing them so that there's B elements in B plus 1 blocks. All right, and then once I'm done that, I can insert, I have space in this block as well as all the rest of them, and I can insert my X in there, and I'm done. So that is called a spread operation, right? Again, you might be tempted to do this in assignment 2, but you don't need to. Might actually be bad if you do. But I haven't tested it. I think asymptotically, you pay a little price for that. But, all right. Questions? Okay. Really need to get into this. All right, let's talk a little bit about officially what we do in terms of the code. So this is my add function. Obviously, if I'm adding to the back, I can just call add X, right? If I'm trying to add to the last location. Otherwise, I grab the current location. I grab the node out of that location. And then I'm going to walk to the right R blocks where, R is at most B. I did not see the dummy, and every block I see is at least B plus 1, right? So these are all 3 of our cases. So maybe I find a block that is not full, then I exit the while loop, or maybe I find the dummy, in which case I exit the while loop, or maybe I count B blocks, everything's still full, In all three cases, I exit the while loop. And then I check to see which case I'm in. So if R is equal to B, that means all of the blocks, B blocks, were full. And so I'm going to make this call to spread. And then U is equal to, I'm going to spread from this block. We're going to see the code for that in a second. U, I've been updating U, so let's see here. I wanted to insert into here, so I have a location, and the location is pointing to this block. And then I say, well, U also points to this block, but then I start marching down the list. So I want to find basically at the end, U is going to point to perhaps the dummy, right? In which case I can start from the dummy, I can insert a new block, and then I can shift everything over. Or U points to some block that has room in it, or I counted B things, and then I call spread, and then I'm going to reset U to here because the reason why I need U over here is if I shift, right? So I'm going to say, I want to shift from, I have to start and shift this guy first so that I do not exceed the block limit. And then I want to shift this guy. So this has B plus 1, and when I shift, it goes down to B, and then I made room in this guy to shift 1 from over here. So I have to start, if I'm going to shift, I have to start on the right-hand side and move to the left, and that's what this U is for. But if I spread, then I don't need to do any of that. I automatically have room in my current block. Perhaps U is equal to the dummy. Then I'm going to add an empty block. And then again, I'm just going to shift everything into that. So while U is not equal to the current location, I'm going to shift and move 1 to the left, right? So that is this operation here. So I'm not going to get too detailed beyond that, but yeah, those are our 3 cases. That's the code for it if you're interested. And then at the end, I should ostensibly have room in this block, so I'm going to add X to that, and then increment N. All right, questions? Okay. All right, so that's our sort of very rough implementation. So what is the runtime of these implementations? Well, cases 1 and 2 means I found room within B blocks, right? So I'm going to shift a bunch of elements. These are array decks from the back of an array deck to the front of another array deck. I'm going to do that at most B times. So if I have to shift in case 1 and 2, it's going to be big O of B time to insert, or sorry, to shift. And then my insertion, made a mistake there, so we lost the graphic, that's okay. Then my insertion into that block, well, this is classic array deck. My block has size B roughly, and I'm inserting in location J, so the array deck, as we know, inserts in this time. Okay, so that's case 1 and 2. O of B plus the min of this. How many elements are moved in a call to spread? So case number 3, that means we've walked B blocks, all B of them were full. So I made a new empty block, and I took all those full blocks and I distributed them. So how many moves does that take? Well, I go from this to 1, 2, 3, 4, where each of these has B. Well, I guess we could use the explicit numbers. So I go from each of them having 4. So I go from 3 blocks having 4 to 4 blocks having 3. And I want to keep the same order, which means that I'm going to shift 1, 2, 3 elements from here into my last block. And then in my next step, which incidentally 3 is B. In my next step, these guys are gone. I have 1C. I want to end up with 3 elements altogether. So I'm going to shift 1, 2 elements from my next block into that block, which is incidentally B minus 1. Now I have these guys are gone. I have 2 elements. I want to shift 1 from here into here. So that's B minus 2. And so for this case, it's easy to see that this is 3 plus 2 plus 1. In general, it would be, if I had B plus 1 in each of these, then I would shift, sorry, this one would be empty. I would shift B into here. I would shift B minus 1 into here. I would shift B minus 2 into there. And then eventually I would shift down to 1. All right, so how much work do I do in a call to spread? Well, it's quite a bit actually, but B plus B minus 1 plus B minus 2 plus 2 plus 1. And so that's just a summation. Another way to write that is I equals 1 to B of I, which is B plus 1 over 2. And if we did big O, this would be big O of B squared. Okay, so that's that B squared is a little bit ugly, but yeah, that's what we get. All right, questions? Okay. So yeah, we move B elements, and then we move B minus 1 elements to the next block, et cetera, until finally we move 1 element out of this U of 0 here. Okay, and that takes B times B plus 1 over 2, or big O of B squared time. And that's nasty, but we're going to amortize it. We're going to show that we don't have to do it too often. Again, using another kind of amortized analysis, slightly different from everything we've seen so far. But if we ignore the calls to spread, then I locate I and then insert its big O of B plus the min of I n minus I over B. Yeah, the B is, so this is finding the location, and this, I guess, would be a sort of a rough bound on insertion, right? I insert into a block of B elements, I might move O of B things to do that. All right, sorry, questions? I mean, this is our, what is it, min of J and B minus J. All right. Okay, so that's our analysis for add. It works if we ignore spread. It's sort of fast-ish. At least there's a bit of a speed up. Removing elements now is going to be very similar to add, but there's going to be basically, we want to remove from U of 0, but we're already down to B minus 1 elements. So technically, we cannot do that without violating the block size. So we're going to do the same thing. We're going to, well, you know, let's say maybe there was enough room to remove something. So I remove the thing. Now there's B minus 1 elements. Everything is fine. Or I cannot remove from this guy, but I'm going to take a walk. And eventually I find something I can remove from. And in which case I'm going to shift a bunch of things over. And then I can remove from the first one, because now there's B elements in that block. And then, of course, in the last case, maybe I walk, or maybe I find the dummy, which we'll talk about, or maybe I walk too far, right? I walk within B blocks and everything has too few things in it for me to be able to remove anything. Then I'm going to do sort of the opposite call of spread. I'm going to do a call to gather. Okay, so that's the basic arguments. So case one, I want to remove from here. I'm going to say B is equal to 3. That may or may not hold here, or general B. Everything's too empty, except I do end up finding a block that I can remove from. So I shift a bunch of elements over, and then I have enough room to remove, and I can remove my thing and maintain the block limits. So that's case one, sort of the easy case. Yeah. Case two, in less than B steps, I find the dummy node. Now, technically, if B is equal to 3, that's not quite what's going on here, but so use your imagination a little bit. The diagram is not quite accurate. But let's say in less than B steps, I find the dummy node. Now, what I know is that this guy can contain less than B minus 1 elements, right? That's allowed because it's the last one. So all I'm going to do is I'm going to shift out of this block. Now this guy has only 1 element, and that's less than B minus 1, but that's okay. I'm allowed to do that. Or possibly it's empty, right? I shift 1 out. Now this block is empty. If it's empty, I'm going to remove it from my doubly linked list. Okay. So yeah. Okay. Case 3, again, I look B steps. Okay, yeah. Yeah, if somebody can send them a link. If you guys, or you can send me a fresh link and I can repost it on Brightspace, either way. Did I post the old one on Brightspace? If not, I'm willing to do that. But okay, so case 3, after B steps, all B blocks have B minus 1 elements. So in this case, we can say B is equal to 3. Each of these 3 blocks has only 2 elements in it. That's not enough. So I am going to gather so that the first, I have B blocks, each of them with B minus 1 elements. I'm going to turn that into B blocks, each of them with B elements, right? So I'm going to take these 3 blocks here, and I'm going to turn them into AAB, BCC, and now this last block will be empty. So this is a gather step, right? So I take a bunch of sort of partially empty blocks, and I gather them into a bunch of blocks with B elements and 1 empty block, which I can then remove. Remove the empty block, and then I can remove the element from U of 0 because I have the extra thing in there. So it's just a gather, opposite of spread. Right. Questions? Right. The implementation you'll see is also similar. So yeah, I gather everything into my 2 first blocks here, or B blocks in general. Sorry, B minus 1 blocks in general, and then I remove that empty one. And then I can call remove on my U of 0. I have B minus 1 in the first and B in everything else, and I'm good. Okay, so here's the code again. I probably will just skip most of this, but again, I'm looking for the, oh, sorry. This is spread. This is different. All right, so that is, sweet, okay. Okay, so that's removing. So now we're going to analyze spread and gather, or at least look at the code a little bit. So spread, I give you a node, and I'm telling you that this node and everything within B blocks is full. So I want you to spread those out by adding a new block. So I take this node U, I make a pointer W, and I walk B steps forward. And then I add a new block before that last one, right? So steps are my B blocks. This is my Bth step. So I add a new empty block before this one. And then I'm going to shift everything until I have B blocks in it, right? So I'm going to say, well, shift from here to here until this has B blocks, and then shift from here to here until this has B blocks, shift from here to here until this has B blocks. And when I'm done, until I get to the original one U, and then I'm done. And then, yeah, that's it. Simple enough. Questions? Gather, again, very similar. But in this case, I am going to in this case, I want to gather, and I've been drawing it so that I go from here to here. I start at the end, but in this case, gather, I can actually start from here because this will temporarily have B minus 2 elements, but then I'm going to add one back. Or add 2 back, actually, right? So these, I can, basically do this in the opposite order. Not super important, as long as you understand the overall algorithm. Again, this is perfect. Yeah. Anyway, questions? All right, after gather, of course, the last W block should be empty, so I can just remove it. Okay, so analysis of spread and gather. Both of these are dominated by this double loop, right? So in this case, I have a for loop for B blocks, and then I shift big O of B elements each time. I mean, it goes from 1 to B, but on average, it'll be B over 2, roughly. And yeah, same with this one. Sorry, here. I have the double loop, right? So I'm going to basically start at the back and then walk my way to the front. And each time I take a step, I shift a bunch of elements, on average B again. So they're both dominated by this double loop. I have B times B plus 1 over 2 moves for spread. We analyzed that earlier. B times B minus 1 over 2 moves for gather, right? So B minus 1 now because, because here I have B plus 1, and I have to move B each time, and then for my B minus 1, I have to move, we just end earlier, right? We end at B minus 1 instead of B blocks. Asymptotically, these are both the same, though. So big O of B squared for both. Okay, so that's my spread and gather. And we're going to amortize that a little bit. It's not going to give us great performance, but basically our claim is that spread and gather execute at most once for every B calls to add and remove. So it's O of B squared operations for every B calls to add and remove. So our add and remove functions in my space-efficient linked list, amortized, run in big O of the B times M for M operations, right? So it's not, we have an extra factor of B now. Yeah, that probably cancels out the cancels out exactly the gains that we made earlier. But yeah, so we're going to sort of prove this is true. Questions so far? Right, so yeah, the big idea is that this is how much time we spend in spread and gather. We're going to show that for every b squared operations, we have b times m calls. Okay, so we're going to use potential to prove this. So a node is called fragile if it does not have b elements, and rugged if it has b elements. That means rugged is sort of resistant to a rugged node I can add or remove from it, right? So it's going, yeah, the idea is that I'm going to make a potential that is the number of fragile nodes. And of course, the idea is that on a call to spread, for instance, I have a bunch of blocks with b plus 1. These are all fragile because they do not have b. And I'm going to turn roughly b blocks, b fragile blocks, into b rugged blocks that have exactly b elements. Right? So that's the idea. And then once I do that, in order to get them all fragile again, I have to do basically b add operations, at least. So that's the big picture. And then you can make a similar argument for remove and gather. But we're just going to do add and spread. And it's exactly what I just explained. So case 1, I found a block with room. Well, then when I'm adding, exactly one block changes size. So my potential phi is equal to the number of fragile blocks. And if I add something, then I can get at most one more fragile block, right? So at most one block goes from rugged to fragile, maybe not, but at most one. Case 2, I found the dummy. I make a new fragile block, right? I add a new empty block, and then I spread into that empty block, or sorry, yeah, I don't spread into it, but I shift one element into that empty block. So I create one new fragile block. It's empty. I put one element in. Again, phi increases by at most 1. These are both calls to add. Case 3, I found b fragile nodes. So at this point, I know that my potential is at least b. And then I'm going to replace these fragile nodes by b plus 1 rugged nodes, which means that phi decreases by at least b minus 1. Yeah, because maybe b. In any case, on order of b. I don't know, my brain stopped working. Possibly that's b instead of b minus 1. But yeah, basically, every time I call add, maybe I make one more fragile block. And then when I call spread, b of those fragile blocks turn to rugged, which means that every time I call spread, I had to make at least big O of b calls to add. So that's roughly the argument. And yeah, so it's not amortized constant time. We're adding in this big O of b for each add and remove operation on the calls to spread and gather. Yeah, I don't know. Questions? I think everybody's. I said this was a very detailed. Today's a day of details. We'll try and go maybe a little lighter on the skip lists, which are coming up next. But yeah. So get, set, and size. Not size. Get and set. Min of I and n minus I over b. Add and remove. Similar runtime with extra b, but then for each add and remove, I also have to pay an extra block size in amortized cost for spread and gather. So that kind of removes this, and I still get add and remove at just basically min of I and n minus I time, amortized in this case. Okay, questions? All right. It's kind of ugly, maybe. I feel like that analysis can be cleaned up a little bit. So let's take a look at our space efficient linked list. It's space efficient. Let's see if it's actually fast. It should be sort of on par with an array deck or something like that. So in this case, I have a doubly linked list and a space efficient linked list with a block size of 4. Seems pretty small. So yeah, of course, our space efficient linked list with a small block size. I mean, I guess that's one other thing to bring up, right? We talked about the runtime, but if my block size is really small, then I basically have a doubly linked list, right? Let's say I have a block size of 1, which that could be problematic, right? Because now I can have a bunch of empty nodes. Probably should put a limit of the block, so at least 2. Since if b is equal to 1, and I'm allowed to have b minus 1 data items in my block, then I'm permitted to have a bunch of empty nodes. So that's kind of a bad idea. In theory, though, if I make a block size of 1, I basically have a doubly linked list, right? And if I have a block size b is n, well, I have an array deck, right? I have a bounded deck, but it's an array deck. And it's technically, if I have one block, it's the last block, so I can have less than n items. It's exactly an array deck. So if I choose a small block size, I should get doubly linked list performance. If I choose a large block size, roughly on order of n, I should get array deck performance. And then in between, I should get the good performance. So this is block size 4. Probably not going to be fantastic, but what do I need for this? No, sorry. Yeah. In file.text. I think it's at 100,000 right now or something. So my doubly linked list, my space efficient linked list is a little bit faster. And what operation are we doing? This is just adding to the back and removing from the front. Yeah, that might cost us here. But still pretty reasonable for a space efficient linked list. It's faster than my doubly linked list. Probably an extra factor of b is helping us out. Let's try a block size of. So if I have 100,000 items, what's square root of 100,000? It's like I don't know. 10,000 is 100, square root of a million is 1,000. Let's call it 500 or something like that. And then remove from the middle. Technically, our space efficient, this should be, well, it's going to be space efficient. It might be faster, it might not. We'll see. Oh, it hates that remove from the middle, eh? Oh, wow, way faster. Yeah, so that block size gave us a good speed up. Even though we're doing the spread to gather, it turns out that that's not very expensive. So yeah, space efficient linked list, also pretty fast at removing from the middle. Using roughly square root square root of n block size. It's, on order of. Good. Questions? Okay. All right, so we have space efficient and doubly linked lists, and now we're going to start with skip lists. I know it's 3 hours, and by the end, my brain's tired. I don't know about yours, but so I'm going to try and keep it a little bit light, and then anything we have to review. I mean, we're not going to get too far this class anyway, but yes, we're going to, maybe I'll talk about some of the larger points, and then maybe we could do a couple of demonstrations. I can show you what I was working on, which actually might become your assignment 3, because I'm finding it difficult. So yeah, so this is the idea we were talking about earlier. You can't start a product simply by building it. Well, I don't entirely agree. There's sort of a category of products that you can do exactly that. But there's more complicated products that you can't do that with. And data structures is one of those, right? So you kind of want to spend a lot of time thinking and a little time programming. If you just program a lot, you're going to make a lot of mistakes. Maybe you're going to ruin something that you did that was actually working. Think, draw pictures, do stuff like that. Okay, so we're going to look at something called a skip list. So this is what the pictures look like, and it's sort of roughly, it's not exactly what it does, but it's close enough. Skip lists are fast, right? So this is it can implement get, set, add, and remove in big O of log n time. So that's way faster than everything we've seen so far. In terms of, well, get and set, we've seen O of 1, but add and remove has always been order of n, roughly. So to put that in perspective, add and remove, the best thing we've seen so far was this min of I or n minus I, and which is, basically big O of n. So if we had 1,000,000 elements, then worst case, adding is going to be 500,000. And if we just add a bunch of elements randomly, then on average, I'm going to have to move 250,000 elements, right? It's going to run slow. In a skip list, log base 2 of 1,000,000 is about 20, right? So from 250,000 down to 20, that's way, way faster. And if I had 1,000,000,000 elements, well, it's kind of hidden, but it would be about 30 memory accesses, right? So basically, the time spent in my skip list is walking through. You can see I basically I have sort of a linked list data structure, but I have a bunch of shortcuts in it. So the key to the skip list is I take shortcuts as much as possible. And if I plan my skip list just right, well, then my paths to find anything are log n. And once I find a node, of course, I can add really quickly, I can remove really quickly, or I can get and set really quickly as well. Right, so that's the idea behind it. Okay, so like many good ideas, it uses randomness. Random, we think of random as bad, but sometimes in some situations it really helps because we can do things on average pretty quickly. It's based on a singly linked list data structure, right? So we only have basically pointers going backwards. There's a couple of twists, of course. So we have what's called a sentinel in the front, which is sort of like the head / dummy node of our list. And we have essentially a singly linked list. But not just that, we have a bunch of lists built on top of that. Yeah, so my sentinel is like the dummy or the head, does not contain any data. This would be null in here. It just marks the front of my list. But then we kind of generalize this idea. So we have a bunch of different lists. So we have list 0, which is my original list. It contains all the data. But then I have another list, list 1, which starts at the sentinel and skips these two guys and lands in location 2, or the location with the value 2, however you want to read this. So as we will see, skip lists, we can implement a sorted set interface, which I guess we haven't seen that yet, eh? So we will implement a sorted set interface with the skip list, but also it can implement a list, a random access list that's really fast. So if it's sorted set, then these are values. If it's a list, then these are indexes. But both work roughly, they're pretty similar. So we have a list L0, we have a list L1, which consists of the sentinel, and then this guy, and this guy, and this guy, and this guy. We have a list L2, which contains the sentinel and this guy, also this guy and this guy, but not the last one. We have a list L3, which contains the sentinel and this guy here. So everything that was in a previous list is eligible to be in the next list, but not all of them are, right? So in order to be in list 3, I had to have been in list 2, list 1, and list 0. List 0 is a given because everybody's in list 0, right? So I have a bunch of pointers that tell me I'm in that list, and I'm not allowed to skip. I'm allowed to skip elements, but I'm not allowed to skip a list, right? So I have to be, if I'm in L3, I have to be in all of these. And that diagram is a little bit deceiving, but it's nicer. It looks nicer than what's actually happening. What's actually happening is that I have a node. I have 4 pointers in this node in an array. You know, my next is now an array of nexts. And 3 of these pointers point to node 3. And this pointer points to node 4. And so the reality is something closer to this, but of course, this looks a lot nicer. So when I say this pointer points to here, I really mean I have access to all of this entire node, right? It's not just that one location. Okay. So it is basically multiple linked lists, where some of the linked lists skip a bunch of elements. Each node has multiple pointers, and it achieves this fast speed by skipping elements. Yeah. All right. Questions so far? Okay. All right, so our node is a singly linked list. Singly linked lists have nodes. This is no different. I have a data element in my node, but now my next pointer is now an array of pointers. Right, so this is my array of pointers here, at least in our diagram. So each of these pointers could point at any element in a further list. My constructor, I make a new array of nodes instead of simply having a pointer. It also has this thing called height. Height is basically the value of the highest list that this node appears in, right? So here I have the length of this is 6, actually, but this is called L0, and this is L1, and up to L5. So we say this has a height of 5, because basically everybody appears in L0, right? So if I have a node that's this is a height of 0. And this guy has a height of 5. All right. There also this is basic node. This is we're going to implement the skip list set first, and then we'll do the list after. So a list has an index. So for the list class, we're going to change the node a little bit. And we're going to add another array, but we'll see when we get there. All right, so every time we create a node now, the idea is we're just going to randomly choose a height, but we don't want it too high. Right? We don't want to waste memory. Of course, there's going to be a little bit of extra memory. everybody's in height 0. So I make, I add an element, I make a new node. I want to figure out what the height is. Well, it's at least 0. And so I'm going to randomly determine the height. And how I'm going to randomly determine it, so I'm going to flip a coin, fair coin. Like you can do that programmatically, right? Just call random int or something between 0 and 1. And if it's 0, that's heads. And if it's 1, that's tails, something like that. Okay, so if the coin is tails, we increment the height. That means I go from being in list 0 to list 1, and then I flip the coin again. Right? And I keep flipping until I get heads, at which point I'm done. So I start here, I flip a coin, I get tails. So now my height is 1. I flip a coin, I get tails. Now my height is 2. Flip a coin, I get heads, I'm done. So this node has height 2. If I flip heads the first time, then my node is simply has height 0. Okay. All right. Questions on that? Cool. What's the expected height of a node? How many times do we expect to flip a coin until we see heads? It's not, I mean, this is, again, a little bit off topic, but do I get to that? I think I do prove that. What is the expected number? We'll come back to that if you're not comfortable with that. It's fairly easy. There's a fairly very straightforward way called the Bernoulli trial. I know this is technically not a probability class, but if I do something until the success condition, which is heads, so I'm basically flipping a coin until I flip heads, or maybe I roll a die until I get 6. And technically, I can keep going forever, right? If I get really unlucky, I just keep rolling and rolling and rolling, or flipping and flipping and flipping, and I never get heads, never get 6. But on average, you would expect, well, if my probability of getting heads is equal to p, which on a fair coin, it's equal to 1/2, then my expected number of coin flips is 1/p. Right, so if this is 1/2, this is 1/1/2, which is 2. And in the case of the die roll, probability that I roll a 6 is equal to, of course, 1/6. So my expected number of die rolls until I get 6 is 1/1/6, which is 6. So it's a nice, again, this is not a math class, so you might get a very, very simple expected value question on the final, maybe. One did appear one year. I'm not really a fan of doing that, but like I said, the math is to help us understand the data structures. It's not a math course, but questions on this? All right. Okay, so on average, we're going to, so the Bernoulli trial is the easy way to do it. We're going to figure out the average height of a node using a more difficult way, but it's a way that is actually, we're going to apply multiple times, so it's useful to learn it. But this means that using Bernoulli trial, if I promote it every time I see tails, and I keep flipping the coin until I see heads, well, I would expect to flip my coin twice before I see heads, which means my expected height of a node would be 1. Right? This is L0, this is L1. This is, on average, every node looks like this. Anyway. All right. We also have a sentinel node, which is the head of the list, and the sentinel has to be, the height of the sentinel is at least as high as the highest node. All right? It's exactly as high as the highest node. Right? We will adjust it up and down. If we get a higher node, or if we remove a node that was the highest, then we will adapt that But the sentinel is always exactly as high as the highest node. And yeah, so the key feature of the skip list, of course, any path to find something is very short with respect to the size of the list. We will see, well, log n, of course, and we will prove that. We'll prove that the expected length of a search path is twice log n plus some constant, which is big O of log n. Basically, we're going to show that the maximum height is on average log n plus a small constant. And well, let's look at the search path first. So how do we find something in this skip list? Well, we're going to start at the very top. We want to skip as many things as possible, so our starting location is going to be the highest list, L5 in this case. So we're going to start it at the sentinel in L5, and we're going to skip as many things as possible so that we still have to be behind the thing we're looking for. If we pass it, we can't go back because it's a singly linked list. I only have forward pointers. But if I can step to here, right? If I'm trying to find 5, then I can take that one big step. That's fine because 4 comes before 5. And so I know 5 will be somewhere after this node. But let's say I call find 4. Okay, well, in this case, I start here and well, it looks pretty easy. I can just jump right to 4 and I'm done. We're going to do things a little bit differently. I mean, this is not invalid, and there are applications that will do this. The way that it's done in the textbook and sort of the way that the ODS skip list works is that it finds the predecessor. So I want to find the thing that's before 4, and we'll see why. Well, I can explain why. If I want to add something to the skip list, if I want to add, say, 3.5, well, 3.5 doesn't exist, but I still want to figure out where it goes. So I have to find the closest thing to it, which is the predecessor. Right? So that's why we do this. It makes adding and removing things like that easier. But also we can reuse this in order to find something. Okay, so we want to find the predecessor of 4. So what are we going to do? We're going to start here. We're going to look to the right and say, is the thing I'm looking for, right? So this is either an index or a sorted list, doesn't matter. I know that 4 is less than 5 and 3 is less than 4. So I'm going to say, is the thing I'm looking for, is the thing I'm looking at, which is 4, less than the thing that I want to find, right? I want to find 4. 4 is not less than itself in this case, right? I'm trying to find the predecessor. So I'm going to say, is the thing I'm looking for less than 4? Nope. Well, I'm going to go down, right? So I'm going to go from L5 to L4. And then I'm going to say, well, in L4, I'm still looking at 4, actually, right? So I'm going to say, is the thing I'm looking for less than 4? The answer is no. Well, now I know I've gone too far again, so I'm going to go down another one. Then I'm going to say, is the thing I'm looking for, did I phrase that correctly? Looking for, is the thing I'm looking at less than 4? Sorry. Is the thing I'm looking at less than 4? The answer in this case is yes. So I can go to the right. And now I'm at this node, and I can look to the right and say, is the thing I'm looking at less than 4? The answer is no, so I'm going to go down. Is the thing I'm looking at less than 4? Yes, so I can move to the right. Is the thing I'm looking at now less than 4? No, and no, and now I found the predecessor. So I found the thing, the greatest thing less than 4 in my list. And then from there, if I wanted to get 4, I can just call, this is a node u, I can call u.next. Yeah. I mean, it's not quite that easy. I think I have to do u.next 0 dot x, and that will give me 4. Okay. So that's essentially the search path. If we were doing something different, let's say we wanted to find 3, then of course, it's a lot easier. Again, that's not precisely what we're doing, but you might see that on a midterm where I say find exactly this instead of finding the predecessor. Either way, I will specify what I expect you to do. Let's say I wanted to find 3. Well, I can say, is the thing I'm looking at 3 or less? The answer is no, so I go down. Is the thing I'm looking at 3 or less? The answer is no, so I go down. Is the thing I'm looking at 3 or less? Yes. And then here it's no. And then here it's yes. And then no, no. Right, so I can generalize this algorithm to find exactly the thing I'm looking for, just by changing whether or not I accept it to be equal to the thing I'm looking for or strictly less than. All right, questions? Okay, so do I have time to? All right, that's the general. I'll leave you with that because otherwise we're going to get too deep into some details. But I guess I can leave you with. Can I run the test? I'll do the implementation next week as well. So it's a neat implementation with a bit of a. Let me see if I can do it. GABC. Skip. Oh, no, sorry. Yeah, all right. I'm just gonna have to recompile everything. So we'll get to it next week because I think basically your assignment 3 might be. So when you search for something, there's a visualization tool here that Robert Collier wrote, and I sort of, I'm borrowing. And so it will print out the skip list and sort of use that format. But now I'm going to say, well, what was the last search path? I want you to sort of highlight that along this thing. And that's what I was trying to do today, and it's much harder than it looks. And I think that maybe that might turn out to be your assignment 3, depending on, I have to look at it for a couple more hours and see if it's the right difficulty. But all right, that's it for today. Don't forget about your, again, the lab is due on Sunday. It's not that long, but it will sort of remind you about some of this stuff. And assignment 2, please get that in because 2 weeks, is it 2 weeks is our midterm, right? So assignment 2 and the midterm are about the same time. So you don't want to be too rushed at that time. Anyway, see you guys later.